All right, guys, this video is going to finish up this section of working backwards. The last video we did 5 and 6. We're going to do 7 and 8. And this is where we're going to introduce, screen up here. This is where we're going to introduce when we have complex zeros or imaginary zeros. And kind of the main thing to remember with this, we took this down before when we did synthetic division. Complex zeros always occur in pairs, right? Because of quadratic form, you have plus or minus. So if a plus bi is a 0, then its conjugate a minus bi is also a 0. All right, so you can never have an odd number complex zeros. So if we look at 7, again, 7 and 8, we're always going to have kind of like the same setup as we did for the last two. We really want to use the factor theorem. So for 7, we want to find a polynomial function that has a degree of 3, but they only give us two zeros here. They give us -3 and 2i. But really, indirectly, they've really given us three zeros because of this complex conjugate, right? If you have complex zeros, they occur in pairs. So you can't just have 2i as a 0. Its conjugate is -2i. Now, in that case, there's no a. It's almost kind of like just saying bi. So if bi is a 0, then -bi has to be a 0. So these are really the three zeros. Now, even though we have I, you might be thinking, well, how am I going to have I in f of x? Eventually, they're going to cancel out. I guess one of the main things we have to remember is that I squared equals -1. That's because the definition of I is really the square root of -1. All right. So when we multiply and FOIL out all the factors, we're going to get an I squared. We're not going to be left with I. That's going to go away. Okay, so if I use factor theorem, the only real 0 we have is this -3. So x minus -3 is x plus 3. Then the other two zeros are the complex conjugates, 2i and -2i. So again, I'm still going to do x minus, but I'm just going to have an I in it. So I'm going to have x minus 2i, and then x minus -2i is x plus 2i. All right. Now, the last problem, I think number 6, I said you can do it whatever order. When you get complex conjugates, it gets tricky. What's going to be the easiest for you is always FOIL out the complex conjugates. When you always FOIL out complex conjugates, the i's are going to go away. If you were to try to do x plus 3 and this x minus 2i, you're going to have i's in it, and it's going to make it a lot harder. So always FOIL out the complex conjugates first. So when I FOIL this out, I have x times x is x squared. Okay, the outer term is going to be positive 2ix. Right, I always write the inner and the outer to the side. The inner is -2i times x, which is -2ix. You can see how these cancel. So that's why we distribute the complex conjugates, because the inner and the outer terms go away. And then the last term we get -2i times 2i, which is this -4i squared. All right. Now this is where I could go back to this. Whenever you have I squared, that's -1. So you can just change the sign that's before. So if this is really -1, when I multiply it with -4, it becomes +4. So this is, I'm just going to change to x squared plus 4. And then I'm just going to bring down this x plus 3. Right? So when you multiply those complex conjugates, the i's go away. Then when I just distribute here and FOIL out, x times x squared is, I'll put it over here, it's x cubed. X times 4 is plus 4x. 3 times x squared is positive 3x squared. And then 3 times 4 is plus 12. All right. And then you can see there are no like terms here. The only thing I would do is just reverse the 3x squared with the 4x, so it's in that standard form. So you start with the highest degree. So we would just say this is x cubed plus 3x squared plus 4x plus 12. And that's our answer. Now, if you graph this one, it's only going to hit it. It would probably look something like this. It's only going to hit it at -3. Let's say this is -3. Probably looks like an S curve, and it looks like this. So this is the only real 0. The other two are complex. All right. Okay, now I'm going to go to the last one. The last one is definitely the hardest one, and it might be the hardest problem that's on your quiz. All right, so there's going to be a lot that I take down. If you have to pause it, rewind it, okay, go ahead and do that so you understand it. All right, let's move it down. Okay, let's kind of focus in. I'm definitely going to need some space here. All right, so find a polynomial function has a degree of 3, and it has 5 and 3 plus 2i is zeros. All right, so right away they try to trick us. They only list 1 0. Make sure that you list the complex conjugate. So implied in this is that its conjugate 3 minus 2i is also a 0. So these are all the zeros. So when I use the factor theorem, if 5 is a 0, then x minus 5 is a factor. Now this is where it gets tricky, because now I have a real and an imaginary part that makes up this complex number. I'm going to put brackets, and I'm going to put x minus, and then I'm just going to put this 3 plus 2i, but I'll put that in parentheses. Just looks kind of ugly. And then the conjugate, I'll put x minus, and then in parentheses, I'll put this, the 3 minus 2i. Now remember, based off the last one, I want to focus on these two. All right, now it just looks so confusing. Here's how we can make this a lot easier, and there's a little trick to it, is if we distribute this negative, we get x minus 3 minus 2i. Same thing here, if I distribute this negative, I'm going to get minus 3, but this is going to become plus 2i. All right. Now here's the little trick, and it's kind of more of a trick just visually, just looking at the problem. Whenever you distribute that negative, these first terms are always the same. The first two, x minus 3 and x minus 3. The i's, since they're conjugates, they're always different, negative 2i and plus 2i. Now let's rearrange this and put parentheses around the x minus 3 because they're the same. All right. Now, here's the little trick. I'll kind of go back. Like if I were to give you guys x minus 3 times x plus 3, you would just get x squared minus 9. Like the outer term would be 3x, the inner term would be negative 3x. They would go away because they're kind of like the conjugates. All right. Now, if you look, I'm going to treat the x minus 3 as one term, almost kind of treat it like the x. So if I FOIL this out, I have x minus 3 times this x minus 3, which is the quantity of x minus 3 squared. Now, here's how I can use a shortcut. If I multiplied x minus 3 with this positive 2i, and then if I did negative 2i times this x minus 3, they're all going to cancel out. And if you listed every single one, you're just wasting your time. The inner and the outer terms cancel out just like they did for this. So then, just kind of like I multiplied the last term, negative 3 times 3 to give me negative 9, I'm just going to multiply the last terms here. So negative 2i times 2i is this negative 4i squared, which is when we make the I squared negative 1, it changes this to plus 4. So we just put plus 4 right here. Okay, and I'm just bringing down the x minus 5. Okay, you can see how this takes a lot of steps. Okay, then I'm going to FOIL this, the x minus 3 out, which would give me x squared, was it minus 6x plus 9, and then bring down this plus 4. Oops. Now just to save space, I'm going to rewrite it over here. I'm going to have x minus 5. Get my face out of the way here. Okay, x minus 5, and then times x squared minus 6x plus, and then 9 plus 4 is 13. All right. Here's another way you could check it. If you actually use quadratic formula for this, the x squared minus 6x plus 13, you should get 3 plus or minus 2i as the answers. So that's how you can check that this is right. This is the hardest part. Then it's just a matter of distributing x to this quadratic and negative 5 to this quadratic. So let's just finish it up. So x times x squared is x cubed. X times negative 6x is negative 6x squared. X times 13 is positive 13x. Okay, then we distribute negative 5. Negative 5 times x squared is negative 5x squared. Negative 5 times negative 6x is plus 30x. and then 5 times 13 there is 65. All right, then we just want to combine our like terms. There's no other x cubes, so that's going to be in our answer. Let's circle negative 6x squared and negative 5x squared. We combine those, we get negative 11x squared. Goes away. We look at all the x's, we have positive 13x and positive 30x. When we add those, we get 43x. Done with that. And then we're only left with this term. We just bring down this plus 65. All right. So these two problems, you got complex zeros. We can still do them by using factor theorem. The biggest thing here is for all of these, you want to FOIL out the complex conjugate factors first, then all the i's are going to go away.